On December 14, 1900, physicist Max Planck developed an equation that described the reason that radiation from a glowing body changes in color as its temperature increases. Contrary to popular belief at the time, Planck's equation implied that energy could only exist in discrete units, much like matter, rather than arbitrary amounts. Said another way, you can divide a quantity of light energy in half over and over again until you reach a small chunk of energy that cannot be divided further. Planck called each of these chunks a quantum. Quantum physics did not really find a prominent place in the scientific world for quite some time. This all changed with the double slit experiment. Let's start with a large-scale explanation of the experiment. If you were to shoot tennis balls, one by one, at a barrier that has two slits and you record with the detector where the balls that manage to pass through the slits impact a second barrier, they would create a pattern much like the one shown here. However, at a subatomic scale using electrons rather than balls, something much different happens. The electrons do not land only behind the two slits as was seen with the tennis balls. Instead, they land across the detector at varying degrees of frequency. Scientists were shocked. They determined the electron behaves like both a particle and a wave, which when reaching the barrier splits in two, releasing separate waves from the other side of the slits. The interaction of the two waves creates the interference pattern at the detector, much like the interference of ripples in water create areas that are strengthened or diminished. This concept of particle-wave duality introduces an idea that scientists struggle to comprehend even today. If an electron is both a particle and a wave, and the wave passes through both slits, the electron must be in two places at once. Yes, two places at once. To better understand, scientists conducted further experiments using detectors. When detectors were switched on, the electrons behaved as particles with no interference pattern. When the detectors were switched off, the electrons were in all places simultaneously. This is known as superposition. To explore the superposition principle further, let's discuss Schrödinger's cat. In this theoretical experiment, a cat is placed in a box with radioactive material that has a 50% chance of decaying and killing the cat. Based on the superposition principle, when the box is closed, the cat is both dead and alive. Only when the box is opened and the cat is observed does it revert to one state. I told you you'd be fine. Quantum physics often seems to contradict common sense, but is intertwined in nearly every aspect of our lives. I can't wait to see where it'll take us next.